neutrino coming from inside the Earth. You know that there are uranium and thorium everywhere inside the mantle and in the crust of our planet. And if you detect antineutrino from this reaction, you can infer how many, what is the radiogenic contribution to the heat of the planet. You know that there are roughly 80 milliwatts of energy that come from our planet. It's not compared to 1.5, 1.4 kilowatt coming from the sun. And we plan also to detect if there is some supernova explosion, antineutrino coming from supernovas. So, the spectroscopy by Kamiokande and the Sudbury start from a threshold that is about 5 MeV, lowered to 4 for Sudbury. We want to start from 2 keV, 200 keV. So, the only way to do that is to employ liquid scintillator, okay? In order to have, the reaction is the same, neutrino of all type, that impinging of electron, the electron is scattered, and in the case of water, you see the Cherenkov light created by electron. In this case, we want to detect light emitted by the electron in the scintillator. Okay, you know the principle of scintillator. I don't know how many experimentalists they are, how many theoreticians. In any case, a scintillator is a medium in which, when a charged particle traverses the medium, excite the electron that compose the atom, and you detect the light emitted in the excitation process, our scintillation port. So this is the spectrum expected for a neutrino. You see that we are able to distinguish between PP, the neutrino, PAP or CNO neutrino, or monoid neutrino, because this is spectroscopy. The scintillation eye allowed for a very low energy threshold, as I said before, 100 kV. He allowed for a good position reconstruction. You can, if you have a three-dimensional detector, see where the events that took place. I show you why this is important. And you have also good energy resolution, because we have a lot of light. While in the case of Cherenkov, we have a quantity of light that is very, very poor, and the solution of the detector in energy is very, very poor. You know what is it? What is the energy resolution of the detector? Yes or no?
Yes, yes.
Yes. Okay. But contrary to the other spectroscopical experiment, you are not able to see the direction of the incoming neutrino, and this is the motivation of Borexino, is that at low energy, and when I say low energy, I mean from 0 to 3 MeV, we have a lot of radioactivity coming from beta and alpha decay. You have uranium, potassium, thorium, you have radioactive nuclei everywhere, and these undergo radioactivity and emitting beta particle, gammas from the excitation of the total nuclei, and also alpha particles. So, if you want to detect neutrino at this very low energy, you have to fight against natural radioactivity. This is why we have high radio purity liquid. How the detector is made in this way: you have a balloon, this one, of 8.5 meter, is a balloon made in vessel, in nylon, which is a vessel made in nylon. The diameter is 8.5 meter and the thickness is only 125 microns. Okay, you imagine it's quite difficult to work with this balloon. In any case, inside this balloon we have 300 tons of liquid scintillator. When I say liquid scintillator, I mean that is pseudocumin, that is a solvent, where we add a solute, that is PPO, in order to enhance the light produced. So when I say scintillator, I mean solvent plus solute, that is PPO. Outside the vessel we have PC without PPO. We do not want that there is light here, only inside the vessel. So instead to add PPO to enhance the light property, we add EMP in order to quench the scintillation. Here are the amount of PC, scintillator plus PC, is on the order of 1,000 tons, 1,030, something like that. And all the PC is contained in a spherical structure on which there are 2,200 multipliers. So the principle is that a neutrino cross the detector, scatter an electron that comports the scintillator, and you see the light by this photomultiplier. Okay? This photomultiplier converts light into an electrical signal, and you can recreate how many light you have produced. That is mean what is the energy of the neutrino and its position. So,
Lino, excuse me. Presumably there should be some mechanical support, or
the sphere in okay. This sphere is stainless steel, and it's set to contain the PC and to mount the 2,200 photomultiplier. And the sphere is kept with this metallic tower, and all around we have high purity water because we want to shield the inner part from gammas and neutrons coming from the rock outside the detector. The detector is inside a mountain, underground. We have almost 1 kilometer and 3,000 meters of rock.
and the density of liquids inside this yellow and outside are the same? Or?
Okay. This one is a pseudocumin. The density is 0.89, lighter than water. So this tower actually do not set to sustain, but to keep the sphere because of the buoyancy. But it's true that there is a slight difference between the inner part and the outer part, because the difference is in this one. PPO and the MP is not the same density, so the density is very, there is a slight difference, and we have to keep it by gauge control, because it's a very, as I said, the nylon balloon is only 125 microns. If you have only a pressure in the order of some millimeter of water, you can crash the balloon. So you have to make a lot of care about. We have also photomultiplier looking outward here in water, because we want to monitor how many for this purpose have to be located underground, because you have to fight against the cotton prey. For example, actually here on Earth we have 1 muon every square meter per second, roughly. If you put this detector in a Gran Sasso, this rotating in a Gran Sasso, the amount of muon is lowered by a factor 1 million. But even if you have only 1 million of muon per square meter per second, is troublesome for the experiment. So we have a mu bit here. Every time a mu cross detector, we account